Hi everyone. Welcome to the FEM at LLNL seminar series. We've been doing this for quite a while. I think we're going to keep doing it monthly. It's been over a year at this point. But at this point, I'd like to introduce Sungho Lee from the University of Memphis at the Center for Earthquake and Research Information. He took his PhD in South Korea on Earth and Environmental Sciences. So it was a major in geophysics, and he is going to go ahead and talk to us about using MFEM for tectonics. So why don't you go ahead and take it away, Simo?
Thank you. Thank you for introducing. Hi. Hello, everyone. It must be morning. So I'm Sungho Lee. Thank you for having me today and this opportunity. I'm happy to share my works with MFEM community. Maybe this is first time to share my things with MFEM community. Today, I'd like to introduce my ongoing project. Actually, this is done by myself. This is using MFEM. I'm a postdoc working at CERI. This is Center for Earthquake Research Information, and just a part of the University of Memphis, Tennessee. In the U.S., this map shows how the seismic active. It is the red means it is highly seismic active. So it is creep, but there are some seismic active region in the state. One of the reason is the western U.S. along the Pacific plate boundary, and also in the center there is a seismic active zone. We call it New Madrid seismic zone in the central U.S. and Memphis located here. So Memphis is located at margin of the New Madrid zone. So CERI is the firstly responsible for monitoring seismicity in this zone and was a excellent center for the Tennessee. Now it is still the center of the Tennessee, and at the same time at a educational institute after CERI is entering the University of Memphis. So we usually obtain this type of data. We call it seismic waveform from the seismometer, which is deployed in the central US, and we do some analysis to get useful information from this type of waveform. So to study seismic waveform or use seismic waveform is seismology. These two diagrams shows the prime example of what seismologist is doing. The left one is the seismic tomography. So it means it shows the velocity difference inside Earth, and the right one shows the earthquake location. We call it hypercenter distribution. So in seismology, we use usually embodied the waveform, seismic waveform, to obtain those type of information to study inside of Earth. But however, we can only capture the present state of the Earth, like this diagram. So this is time, this is past, this is future, this is present, and this is space. So we can get only a piece of the information. So to study evolution of the Earth, we need the four numerical simulation. Speaking of Earth's evolution, I should introduce a pioneer. His name is Alfred Wegener. He's a German meteorologist, and he proposed continental drift. Here, the drift means the moving. So continental is moving around. However, his idea was not accepted when he was alive, unfortunately. After people discover the ocean floor, this image shows ocean flow is ocean flow was really spreading, and Wilson integrate a model describe opening and closing of the ocean basin, as well as the subduction and divergence of tectonic plate. People started to adopt the plate tectonics. We have discovered many major plates and microplates and US on the North America plate here. And those plates floating on the mantle and moving around. And Earth is composed of several layers, but mainly 4 layers. That is first mantle, and outer core, and inner core. And outer core is mainly liquid state. So the shear wave, the shear wave cannot penetrate into outer core, and the rest of layers are solid state. However, if you just behave like ancient church, like windows in church usually have thicker base. So over long period, solid material like behave like the fluid. Particularly, mantle has relatively low viscosity compared to others. And additionally, the top of the mantle is relatively cold, and but outer core, the top of the outer core is very hot. So there is thermal instability. So also has quite wide dimension in terms of the volume, and viscosity is, I said, is relatively low. So it is sufficient for its convecting. So matter is convecting. So if we calculate the Reynolds number is already much beyond the critical state. So mantle is convecting in very slowly. In my committee, I have access to modern server simulating mantle convection and lithosphere dynamics. The server name is Aspect, and it is based on Build2, which is another FEM library like MFEM. This code assumes the slow-moving and incompressibility flow, so it only solves the Stokes equation. It may always solve the instantaneous state. However, for some reason, this is video show how the earthquake is the earthquake mechanism, but for some reason it is not working. I'm so sorry about that. Anyway, I'm interested in studying earthquake mechanism. Originally, this video shows how earthquake happen. Earthquake release the accumulate elastic strength. So elasticity is necessary, but the mantle convection code incompressible there it doesn't consider elasticity there. And also my community have another code that its name is FEM. This code can simulate the wave propagation. This is SEM code, so spectral element matter using high order element. But this can only simulate the wave propagation. This is in second scale or the minute scale. But I'm interested in evolution of some tectonics. So I need some like the bridge between the long-term and short-term, because geological process span short-term to long-term scale, like this fold. This fold is involved with the thousands of the short-term events. However, connecting the second scale to like the geological scale, the million scale is super challenging to simulate in terms of numerical simulation. And also it already beyond the the small strain assumption, I need some moving frame as well. To do that, I have to use two special numerical treatment, which are known as LAG. LAG stands for fast Lagrangian analysis of continua. This idea was proposed around 1980s. So FLAG used explicit time stepping. Basically, when it calculates the current velocity, it used the previous velocity and current force and damp out damping force here. And damping force is determined by the magnitude of the current force and sign of the velocity, and take the opposite sign to current velocity and a portion of the damping factor. So this video shows how the dynamic relaxation occurs. So first time there is vibrating, but if the just time being, it can reach to quasi-static solution, just by introducing damping into Poisson equation. Additionally, I introduced a fake or fictitious density to achieve the long time stepping. The FLAG uses explicit time stepping, so it means every time stepping be satisfied with the current condition. So by introducing very large mass, which slow down the P wave velocity during the slow movement, and we can turn off the mass, this kind of mass scaling when earthquake occurs. Okay, this is a brochure of the FLAG 3D. This algorithm is implement some codes, and one of them, FLAG 3D, is very successful commercial solver using academia and industry as well, particularly geotechnical engineering and geomechanics. There is another server, another code. This is the sister code of the FLAG, the dinosaur. This is also the movie, but for some reason it is frozen. I'm so sorry about that. And this is open source code. It uses triangular and tetrahedral element, and also it has capability of the remeshing using MMG, and utilize OpenMP and OpenACC. However, this is very hardwired to particular type of element like the tetrahedral and triangular, and only allow for serial calculation. So I need some more flexibility in FLAG algorithm. And I found MFEM and LAGHOS. I'm a user of the aspect, the mantle convection code I introduced. As I mentioned, it used the DL2. So building aspect, at first time, it was really challenging task for me because it requires many dependencies. So it takes more than hours to build it on my PC. Even on a cluster, it's more challenging. However, MFEM is very lightweight compared to DL2 and LAGHOS, which is mini app already. It has what I want. So I adopted LAGHOS to develop my code. I named my code LAGHOS, which stands for Lagrangian High-Order Solver for Tectonics, giving like the impression that LAGHOS is this sort of the LAGHOS. Here is my hand-drawn logo for LAGHOS, and this is a wiki page of the LAGHOS. On my GitHub, you can check my implementation and benchmark test. Excuse me. Okay. To implement the last step, I won't go over the detail of the communication here. I just introduce what I did. I add I modified the stress tensor considering Hooke's law and introduce the body force here. Also, we need the stress change, stress rate. So I introduced Zalman's stress rate here to be free from the frame, and solving the equation using LAGHOS. And I added the stress update, which can be done either in fully or partially assembled form. Okay, after implementing elasticity, I tested several benchmarks, and I like to show I introduce my benchmark works. And this is first one. I use the same example of this is the shadow blast weight problem in LAGHOS, problem number 1. I call it blast in elastic box. The left one shows the region of the LAGHOS. Maybe you guys are very familiar with it. And right one is the numerical region of the LAGHOS. So this is like the situation. We hammering on like elastic plane, and there is sudden energy blast, and it propagates, and we get some seismic waves. So you can see the vibrating of the medium here. So I like this example. It looks cool. And I mentioned implement body force in stress tensor. So to verify my implementation, I prepared this problem. So this is my problem. So this is column. So the bottom is fixed, and the left and right boundary is the free split. And the gravity is acting on in downward direction, and top boundary is traction rate. So if everything is zero states, so it must be consolidated due to the body force, and it should be reached to the lithostatic state. So I simulate that situation. So you can see some vibrating of the column, and it reaches to quasi-static, and you can see the lithostatic state. So vibrating and stop. And I compare with analytic solution. So this is displacement of the particle displacement. This is the particle stress, the sigma YY component, and that is density. Because the LAGHOS solve the volume change exactly, the mass balance. So density should be increased at the top. So we can see also density variation over the height, and displacement and shear stress looks good, but density has show little like zigzagging pattern. Maybe this rise from the parallel view issue because I extract the data from the parallel view, but I haven't looked at it after I benchmark it, but I will figure out later. So if I just figure out, I will let you know later. And this is the second, this is the benchmark. So we call it odometer test. So this box is compressed by a constant velocity like this. So we can expect linearly increase the displacement like this, and horizontal stress also increase according to the displacement increase. So this black line is analytic solution for elasticity, and the yellow circle from the LAGHOS region, and it has very relatively low error here. So I believe the elasticity implementation elasticity is well implemented, and you can see the details about the analytic solution. How can I drive something like that on my GitHub? And rock has yield strength. So when stress exceeds the yield strength, the failure occurs. So there are several models to predict plastic failure, and rock often follow the pressure-dependent failure model. So the Drucker-Plugger and Mohr-Coulombs are commonly adopted in my community. I believe Mohr-Coulomb is considered more reliable because it is well matched with the lab data. So I adopted Mohr-Coulomb model. And I don't know, you guys familiar with this type of the diagram? We call it Mohr circle. So using the principal stress, this is sigma 1, this is sigma 3. I can draw Mohr circle like this. And additionally, I can plot the failure, the criterion line using this equation. Tau is shear stress and the sigma n is normal stress. Mu is the slope. This is frictional coefficient. And C is intercept of the Y, that is the cohesion. So if the circle, this circle bisect, intersect of the line or touch the line, the failure occurs according to Mohr-Coulomb theory. So exceeding this stress should be reduced at least onto failure envelope. So implementing return of this overstress to failure envelope numerically is called return mapping. Additionally, since we don't have the constitutive law for plastic failure, so there is no relationship with strain, the plastic strain and plastic stress. So we assume it follows the shortest path like this. In geological media, two types of the failure occur. First one is shear failure. The other one is tensile failure. So shear failure occur like this slip, and tensile failure is mode 1 the failure. So we have two types of the failure. So to distinguish them, I need another function that is the diagonal line. So this diagonal line defined by this function. So using three function, I can distinguish this is shear failure, this is tensile failure. Okay. And theoretically, shear motion cannot cause the volume change, but it occurs in reality. So this phenomenon arises from presence of the asperity and the grain rearrangement under the loading of the shear loading. To account for this effect, I also introduced the dilation angle chi, which is generally smaller than the friction internal friction angle. So I reuse the previous benchmark again, considering the plastic failure. In either case, whether the two angles, so friction angle and dilation angle, identical or different, it is well matched with analytic solution. However, in reality, return mapping does not occur instantaneously. It is more complex mechanism involving some time-dependent characteristic. Therefore, I introduced rate-dependent model by incorporating certain time scale or viscosity. So model 1 represent rate independent, but model 2 represent rate dependent model. Due to the viscosity, stress does not return right back to model failure envelope. Instead, the stress relax, and then because the stress evolved over time, it means the failure state also changed. So that's why if we introduce rate dependent model, the path is also changed compared to rate independent model. So it takes several time to the overstress model return to the failure envelope model. So, but if the viscosity infinite, so the time scaling is infinite, the material behavior like the elastic material. So the overstress cannot go back to the failure envelope. But if the viscosity is 0, it is exact same with rate independent plasticity. The rate independent model, this type of model is known to be highly sensitive to numerical mesh size. So if the mesh to become smaller and the shear band to shrink. So, but Lagrangian is involved with the mesh change. So shear band goes to 0. So it is kind of issue, the numerical mesh issue. So to resolve the issue, the rate dependent model is suggested. And so that's why I implement this feature 2 model. And this is benchmark for rate dependent and rate independent model. Unlike the previous example, I impose my boundary velocity on the top. So this model simulates the simple shear case. So you can see the material is shear by this velocity model. So the pink line represents elastic case. So model increase of the displacement model means the shear stress also linearly increase like this, and numerical solution is very overlap with analytic solution model. As a counterpart of the elastic case, it's the perfect plasticity. So at some point, the failure occur every time. So it is under this surface. And I also tested between the model and member elasticity and perfect plasticity. Yeah, LAGHOS shows the numerical solution is very well agreed with analytic solution here. Model. And the crust, I said, it is on the top of the mantle, and mantle is ductile layer. So bottom of the brittle layer, it can also deform. So I cannot use free slip on the boundary model. Also, the ductile layer can penetrate or can be pushed out according to, depends on the stress state. Therefore, I introduced the spring boundary condition, aka the Winkler foundation. This boundary condition can prevent the sinking of the media and allow the bottom domain to be free to deform. So, model. Okay. There we go. So it sync, but at some point it does not sync anymore because I add this type of the force on the bottom boundary model. The previous slide is all about the geological application. I prepare one example simulating the evolution of normal fault. I consider the crust. It has 100 kilometer of the width and 10 kilometer of the height. At I impose at rate of 3 millimeter per year on each left and right side, and I impose a weak joint model as it is for to keep the initial for development model. And we can observe this setup in Atlantic Ocean. Middle ocean rates is continuously evolving and forming the new crust in real time. Additionally, this is Iceland. The middle ocean ridge runs across mainland, and you can observe the basin formation due to evolving the ridge here. And in the field, the intact rock, the intact rock means the fresh rock. So no damaged rock. So intact rock exhibit the strain cohesion, but the fault is almost cohesionless. Therefore, strain softening is typically observed in the field. I considered this scenario, so I impose like this the simple linearly model strength decrease according to shear strain model. And this is properties, material property I use for this simulation, and those values represent the cross property here. Model. And this video demonstrates normal evolution or ridge evolution. You can recognize somehow at some point it needs remeshing and remapping, but promising is I can simulate till almost 1 million years. That is really promising to me. But the LAGHOS calculate the minimum length, and initially it was around 600 meter, but it goes to like 1 meter at 1 million. So remeshing and remapping require, because the length scale is used in determining the time stepping size. It means time step size goes gradually decrease to satisfy the current condition here. So I implemented the remeshing using TMOP target mesh optimized paradigm, and also remapping, the interpolation for H1 using GS-Leap and L2 for the RAMOS onto the new mesh. So this is the result, the remeshing and remapping. So the first one is after remeshing, the mesh change a bit and it looks good. And also at the same time, top and bottom boundary maintained after remeshing. The TMOP requires some boundary condition. It's free slip. Also, it can be the fixed boundary condition. So if you use the free slip, the top and the bottom boundary can be changed after remeshing. But my remeshing scheme used to maintain the top and bottom boundary because I used the remeshing twice. And between the remeshing, I use interpolation again, but I won't cover the details today. Anyway, I remapping H1 using GS-Leap and L2 for the RAMOS, but I realized my model has some instability on the non-conforming boundaries. So I test the remapping capability of the RAMOS using the with NC-MESI. I think this is my personal opinion. RAMOS is not working correctly on NC-MESI, but LAGHOS is good with the conforming mesh now. So this what I prepared today. So my future plan is enabling calculation in CUDA. Originally, LAGHOS is running with the GPU, but for some reason my calculation is not correctly with the CUDA. I found some vector is not added to right-hand side correctly, so I'm working on that. Also, the thermal energy is the primary driving force for the tectonic, the plate tectonics. So I should implement the thermal energy in future. Also, like complex rheology, like the creep, the dislocation or diffusion creep, something like that. Yeah. Thank you.
Excellent. Thank you. Can we give let's give Sungho a virtual round of applause here. It's an excellent talk. I've got a few questions, but does anyone else want to chime in before me? there's quite a bit to talk about actually.
Model, 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 model.
I'll go ahead and ask one of them. So yeah, you've absolutely done some very thorough work. I like how you every time you added kind of another term, you actually had a specific test to test that term.
Yes, exactly.
Yeah, so you could make sure you were in pretty good shape. One thing I wanted to ask about, you were doing like critical strain failure, and I think you had a couple different kinds of material failure in there. Have you looked into more sophisticated failure models like Johnson-Holmquist or failure models with actual material history in them?
Uh, model Johnson
Johnson-Holmquist is what's a ceramic model, so it's probably I did a lot of work in material failure a long time ago, but mostly with materials like metals and ceramics. So I'm not quite sure what the sophisticated failure models are for geophysics and for rock.
Okay. As far as I understood, metal is mainly governed by non-pressure dependent plastic model like bond physics.
Yeah.
So, but I said the rock is governed by the pressure dependent. So you can see the coin shape. So there it is the axis of the three principal stress, and the diagonal axis is pressure. And you can see the cone is increased with the pressure. So mainly it the rock should be depend on pressure dependent plastic model. And there are some model, the complex model, but the Drog-Plugger and Mohr-Coulomb is commonly adopted in my field. Maybe for the metal or ceramic is not for the rock type of the plastic barrier.
Yeah, in metals you're usually failing in tension rather than in compression, so it's sort of a different situation. I don't know what the state of the art looks like for rock, honestly, but yeah, it's interesting. Another question I had was, is LAGHOST open source? Could we take a look at this if we wanted?
Yes, sure. Yeah, I open my LAGHOST on this GitHub. So this
there you go. You did have it there. Yeah, okay.
Yeah, I putting the LAGHOST.
Yeah. I missed that was on GitHub. I was looking at your picture of your ghost there.
This is really cute.
Yeah, that was cute. Any other folks have some questions?
I posted the link. I also found it. I wanted.
He's at it.
I'd like to echo. It's very impressive. You managed to combine quite a few of our technologies: LAGHOS, REMOS, TeamUp, remap. It's very fine points.
AMR.
AMR.
Yeah.
I don't know. You said that REMOS with AMR currently does not work.
We should look into that.
That shouldn't be the case because we do use remap with AMR, but maybe REMOS hasn't been updated for that.
My finding is when we use like non-conforming mesh with the REMOS, the L2 variable should be affected. But for some reason, between the non-conforming boundary hanging node, the data is not affected. So for some reason, it is blocked with the combination of the high order and low order solver together. So when I doing my experiment, I turn up the low order solver. But if I turn up the low order solver, it drives a lot of the errors there. So the data, the balance of the before remapping and after remapping, there are huge of the error.
There might be a call that you're missing or something like that too. So we'll have to look into that. That there might be a simple workaround here.
Yeah, thank you so much.
Yeah.
And this is just basically DJ with the MR that needs to work correctly. And this has to do with base terms that are on this boundaries. It should. Yeah, we should take a look.
Thank you so
One
much.
question I had is, I know you mentioned that.
All my calculation done with the parallel.
So how large have you scaled it to? What are the biggest sizes or English rates?
Honestly, my PC has only 64 cores, and my university, the cluster always is so busy. I cannot put the last huge job there, so I haven't tested it.
You could use access to a real cluster, it sounds like.
Yeah. So I'm really wondering the LAGHOS has good the parallel scalability or
Yeah, LAGHOS does, but yeah, it would be interesting to see how far LAGHOS scales for sure.
And in terms of order, what orders are you using?
This is Q1 mesh.
Have you tried higher? Do you want to try higher?
Yes. I tried to hire older mesh, but there is some problem. I implement the plasticity image. Dislocation happens when the failure occurs. So if the dislocation is large, the high order element always shows negative Jacobian. So my model is crashed. So that was I have to solve it. Yeah. So I'm also working on that. So what is a higher order element merit in LAGHOST?
Okay. Thank you.
Yeah, you've done. You've kind of done this as a one-man band, so there's a lot of work in here for sure for one person, and it's like I could see you're trying to chase down the bugs as fast as you're running into them. Does anyone else have any other questions? Otherwise, we'll go ahead and wrap it up. Let me go ahead and turn it around. Do you have any questions for us, Sungho?
Yeah, to be honest, when I get the like proposed my talk to your MFEM community, I really want to thank you guys because I posted a lot of the questions on MFEM wiki, and also the LAGHOS wiki. Always you guys very prompt to respond my question. So I always think about that. So I feel like I have to feedback something to you. So that's why I decide to present my work. And also I'm really happy to share my work, and please keep sharing my work. I have a lot of issue. Maybe I need some help from your expertise. I'm not like mathematic guys. I'm geophysics, so I'm more involved with the data. So the numerical simulation is beyond my expertise.
Well, you've done a lot of good work here, especially considering you're not really a numerical physicist. So that's excellent. And thanks for calling out like the teams, how much the team has jumped in there and helped you. It's really good to see that people are getting help online, and our folks are really good about jumping in there, especially when we have someone who's like, oh yeah, we understand that, they'll just jump right in. So it's really good to hear that you had a great experience there.
Thank you.
Thank you, Sungho.
All right.
Thank you so much.
So I'm going to go ahead and call it a close. Sungho, if you could go ahead and send me these slides, I'll go ahead and we'll go ahead and get those posted on the webpage, along with the video of this on YouTube eventually. But again, thank you for taking the time to present this to us. And I look forward to sort of following this work in the future. And I'd love to see a very large scale 3D simulation out of this. It makes some awesome pictures, I'm sure.
Yes, sure. I'm going to share my slide, and okay, I will image you.
Wonderful. Thank you so much.
Okay,
Thank you.
bye. Good luck.
Bye bye.
Take care.